Hey everyone, I'm Chris Okamura, and we're Team 10, and our project was to use data augmentation to improve underwater SLAM performance. So our project motivation was that underwater SLAM systems face a lot of difficulties with obtaining good data because of very harsh conditions underwater with turbidity and poor visibility, bad lighting. Our contributions were to answer this question. Can artificially adding texture to a video stream improve performance in underwater SLAM? So for experiments, we ran OrbSLAM 3 on three versions of the input dataset, which we each augmented in a different way using different models. To evaluate, we use standard metrics and visualizations to see which method and augmentation approach produces the best estimate. For laid works, we built off of Twilight SLAM. This group aimed to improve SLAM performance in low light conditions, and they use multiple machine learning models to improve the SLAM performance and evaluate the impacts of different brightness enhancements. Our goal was to extend these augmentations and use them and see if they work underwater, to see if the same poor lighting visibility also extends to underwater environments. Secondly, we used this other group. We built off of their goal, which was also to improve SLAM performance in underwater environments. Their approach was to combine detail enhancements, contrast in their algorithm. However, for us, we are trying to assess different augmentations that Twilight SLAM used, and we want to see how they individually impact the enhancements for underwater SLAM, or SLAM 3. For our methodology, this is our block diagram. Our output was 8 different trajectories, each generated uniquely. With our raw video stream, we passed them through our 3 different models, test them individually, each with visual OrbSLAM 3, and also with visual inertial OrbSLAM 3. We compared the results there. For OrbSLAM 3, it's a very open source algorithm, which is very accurate. There are 3 main things with the tracking thread, essentially estimating the real-time robot pose given sensor data and the previous map. The mapping thread then taking that estimated pose and refining the map, given the most likely features that it finds. And lastly, closing the loop and map merging by optimizing an essential graph that SLAM built out.
Hi, I'm Daphne. I'll talk about the dataset that we used. We used the Aqualab dataset, which is tailored for underwater SLAM research, and it contains information such as stereo image pairs, IMU data, and ground truth poses, given in both raw file and raw spag files. The dataset was collected from the harbor and archaeological sites as seen in the images. For our project, we used data from the harbor sequence. Underwater imagery often contains scattering and absorptions of light, which significantly affects the performance of visual SLAM systems. This is something we saw in the Aqualook dataset. Data augmentation is a powerful technique to increase the quality of these images. For our project, we applied 2 different augmentation techniques. The first one is contrast enhancement. As seen here, it is a simple affine transformation which scales the difference of brightness to the mean by a predetermined alpha amount. To address this, we employed a PyTorch contrast adjustment functionality. It adjusts the contrast of an image by scaling pixel values around a mean luminance. Contrasted images were generated in both grayscale and color, as seen in the bottom center and bottom right image. The second augmentation technique we applied was brightness enhancement. For this, we used 2 models, the first one being EnlightenGAN. The image shows the architecture of this model. It is a generative adversarial network designed for unsupervised deep light enhancement without paired supervision. It contains dual discriminators to handle different lighting conditions, making it particularly effective for spatially varying underwater lighting. The second model we tried was 0DCE, and the image shows the architecture of this model. It formulates light enhancement as a task of curve estimation using a DC net to iteratively learn a best set of light enhancement curves. This model adjusts the exposure of an image by dynamically predicting a set of curves, and the curves are applied to the input image to adjust the brightness adaptively. This is crucial for handling uneven lighting commonly found in underwater images. Here are some results from the brightness enhancements. In the bottom center, we see the brightened image outputted by the EnlightenGAN model, and the bottom right contains a brightened image outputted by the 0DCE model.
Hi, I'm Tiffany, and I'll be discussing our results. In our first experiment, we evaluated SLAM performance with and without sensor fusion. Visual SLAM estimated the trajectory solely from the monocular images, while Visual Inertial SLAM additionally considered IMU data. We evaluated both methods on 3 metrics assessing the full transformation error, which considers both the translation and rotation of the estimated trajectory. Across all metrics, Visual Inertial SLAM had significantly better performance compared to Visual SLAM. Our next experiments assessed how image augmentation affected the performance of Visual Inertial OrbSLAM 3. We report the full transformation error on 3 metrics. Compared to a baseline with no augmentations, EnlightenGAN and contrast enhancement improved performance while 0DCE reduced performance. Interestingly, the 2 brightness enhancements had vastly different results. To determine why this is the case, we visually assessed images from EnlightenGAN and 0DCE, and we determined that 0DCE improves brightness at the expense of contrast, which we hypothesize is why it performs worse. To supplement our quantitative performance analysis, we also visualized our results. From left to right, these plots show results from Visual SLAM with no augmentation, then Visual Inertial SLAM with no augmentation, and finally Visual Inertial SLAM on images run through EnlightenGAN. These plots depict the ground truth trajectory as a dotted line and the estimated trajectory in color. We see that using IMU data brings our estimated trajectory significantly closer to the ground truth, with image augmentation further improving the trajectory. One limitation of our work is that OrbSlam-3 experiences loop closure failure on the Aqualock dataset. We found that the left side of the underwater environment is a very low texture area, making visual feature extraction inaccurate and unreliable. This caused the robot's depth estimation to drift significantly, ultimately resulted in the mismatch in the objects you see encapsulated in the red circles. Even though they're the same object, because the robot's estimated depth drifted, and therefore built the mapping correctly, place recognition failed and prevented loop closure. This causes catastrophic pose estimation failure. Now I'll discuss the conclusions shown by our results. First, visual inertial SLAM significantly outperformed visual SLAM. This demonstrates the difficulty of estimating trajectory from only monocular visual input and underscores the importance of utilizing all available sensor data when running SLAM, particularly in underwater environments where the images have very poor visibility. Next, two of our evaluated augmentations improved performance, namely brightness enhancement with EnlightenGAN and contrast enhancement. This finding confirms our hypothesis that brightness enhancement and contrast enhancement can both be viable avenues for improving performance in underwater SLAM. In addition, when Twilight SLAM evaluated low light above ground environments, they similarly found that EnlightenGAN improved performance while Zero DCE did not. This supports our hypothesis that underwater environments and low light environments face similar challenges and can potentially be addressed similarly in SLAM methods. This slide discusses potential directions for future work. First, we believe we can further improve performance by fusing depth sensor information using a Kalman filter-based approach. When visual odometry fails due to low texture, depth sensing can act to correct IMU drift in the depth axis. This will have positive downstream effects, as loop closure failure will be less likely if we limit depth drifting. Second, we believe we can improve performance by utilizing stereo vision to obtain RGBD pixel values. This extra dimension of depth information can be leveraged to estimate more accurate frame-to-frame transformation matrices, resulting in more accurate trajectory information. This slide shows our references. Thank you all for listening.